Thanks to Xiaopeng and Elena for inviting me, and I'm very happy to present my research on stochastic calcium signaling and alternans. And this work is done in collaboration with Enrique Alvarez and Blas Echevarria at University of Barcelona, and a student of mine, John Spalding, who is now at UC Riverside. All right, so let me give you an overview of my talk. Okay, so I'm just going to give a very brief introduction to alternans and cardiac arrhythmias. Since people have talked about it yesterday, I'll be very brief. And then I'm going to focus most of my introduction on the stochastic calcium signaling in heart cells, and then argue that alternans of calcium cycling occur in a very particular way, which we refer to as an order-disorder phase transition. And then I'm going to spend the last part of my talk talking about how calcium signaling at the molecular level can explain features of can explain alternans that we see. And feel free to interrupt me if you have any questions. All right. So the basic motivation for our for this work is basically that when a person undergoes fibrillation, they have a normal heart rate, and then something happens here, and then you transition to ventricular tachycardia, and then subsequently fibrillation. And the fundamental question is what is responsible for this VT initiation, and what are the mechanisms? And one of the mechanisms has been alternans. And the basic idea is, as people talked about yesterday, was that alternans induces spatial-temporal heterogeneity in the heart. And because of this heterogeneity, in this case, action potential duration, you can form reentrant patterns on a dynamical substrate as opposed to a fixed heterogeneous substrate. And Elena has done some very nice work, and also Flavio, showing spatially discordant alternans in real hearts, in this case in the rabbit, and showing beautiful nodal lines, the lines separating out of phase regions, and how they're really relevant in a lot of arrhythmogenic conditions. All right, so now the question that I'm going to focus on is, what is the underlying mechanism for calcium alternans? So essentially, if you look at the fluorescence, whole cell fluorescence of calcium in a cell, under certain conditions, obviously, it can alternate, where you have a large release and followed by a small release. And the question is, why does that happen? And can we understand the mechanism from the subcellular scale in terms of the molecular, in terms of the ion channels that are involved, which regulate calcium cycling? And obviously, in order to understand that, we'll have to understand the architecture of calcium signaling. Okay, so I'm just going to review just the basic features. The basic features of calcium signaling, and essentially the main, one of the main findings which people discovered in the mid-90s was that calcium is released at thousands, about 10,000 local release sites in the cell. So this is a 10 micron section of a cardiac cell, and you see that when calcium is released, that it's actually due to the release of these thousands of release events at these junctions, and the question is what is happening at the subcellular level when this happens. So the basic architecture is as follows. Essentially, what you have is you have a cell membrane, and the cell membrane is regulated by voltage, and when voltage rises during an action potential, these L-type calcium channels open and inject calcium into a region here, which is roughly about 10 nanometers by 100 nanometers in diameter. And that region has a lot of what are called ranitidine receptors. So there are about 10 to 100 of these channels in a closed packed network array near the L-type calcium channel. And basically when calcium comes in, it induces the opening of these channels, and then there's a very high concentration of calcium outside. That calcium is released, okay? And when that calcium is released, you form what's called a calcium spark. And a calcium spark appears in this image as one of those bright puffs. Because here they put a fluorescent dye and they measure when the calcium concentration rises, and you see it's a local event, and it's happening at this length scale in several thousand of these junctions. Okay, so that's the basic physiology of calcium release during an action potential. All right, so now the question is how does all this relate to alternans? And in order to understand that, several groups have developed models of calcium cycling, and in fact, in recent years, people have developed models where they account the full spatiotemporal properties of a cell by actually modeling all the compartments in one of these junctions. Okay, and it's a very straightforward method. You basically divide it up into compartments, and you keep track of the calcium concentration in all these compartments. Each of these channels is modeled, via relatively sophisticated Markovian models, which determine how those channels are gated. And so these are the basic equations, which is in the Restrepo-Karmo model from 2008. And it's essentially a compartmental model which keeps track of all the flow of calcium between these junctions. And these are very they're relatively complex models. And the key aspect of these models is that the currents are stochastic. And for example, the amount of calcium released by the RYR channels is dependent on the number of open channels. And these are modeled in a fully stochastic method. In our particular simulations, we use Gillespie's tau leaping algorithms. So there are all sorts of stochastic algorithms to model all of these, the gating of these channels. And in our case, we reduced the Restrepo-Karmo model to a two-dimensional model just to see what happens. Can we understand alternans in this 2D network? And in this case, it's just a brute force, just simulate the system and pace it and see what happens. And indeed, when you pace the system, you see that indeed the global average, the average calcium concentration in the cell alternates from beat to beat. Now, what happens locally is that at a local junction, so this is the calcium concentration at one of these units, at the 100 nanometer scale, that you can have a spark, and no spark. So you have an alternating. You have this very stochastic response at the local level, but at the global level, it's a nice alternating response. If you look at the global signal, you have a nice bifurcation diagram that we would expect for calcium cycling. So the bottom line here is these models reproduce the basic measurements of whole cell calcium. But what's interesting is that the local signals are stochastic, so you really have to develop a stochastic theory to understand what's happening. And this is consistent with Alain and Juan Restrepo had shown similar patterns all the way back in 2009, and Rovetti and in the UCLA group had also done the same thing, and everything was consistent. But the question was, why does this happen, and what is the mechanism? Yeah. How big is? Oh, well, in this case, it's we just sum over. So in this case, it was about I don't say it here. It's about 100 by 100. You could do a 100 by 100 array, or even 1,000. We've also done 1,000 by 1,000, depending upon. Well, you would see it. You would see it. If you simulate like a 100 by 100 system, you would. Sorry, not 1,000 by 1,000. If you simulate a 100 by 100 system, you would see it basically as you pace faster and faster. At some point, the transition happens. And if you do a 20 by 20, 30 by 30, same thing happens. The transition point will shift, but you see the same basic phenomenon. But obviously, you have to do some tuning, and that's the thing. Is like you can see this. well, yeah. So for example, here, if you pace at 250 milliseconds, your transient will be periodic, and you go slightly below, and then your average your average signal will alternate. Yeah. Right. No. When the bifurcation occurs, the KL is only the index. I'm summing over all my units. So KL is just. Oh, okay. Well, I don't know. It depends. I'll answer that in a very precise way. So you have to do what's called finite size scaling to determine how it depends on your system size, which we did. Yeah. Oh yeah, you get the random activity. You're always getting random activity, but when you sum it up and you average over this like 10,000 units, it averages out to a constant. But somehow there's something that happens at this pacing rate when suddenly your whole cell starts to exhibit an alternating response, and which is exactly the interesting question. So, and I'll address the system size dependence of this phenomena. All right, so basically what is happening in the system, and our approach here was to define a local order parameter at each site of our two-dimensional cell model. This local order parameter is simply the difference in the SR calcium concentration from one beat to the next, multiplied by -1 to the n, and I'll explain why that's important a little bit later. And essentially, so we define this order parameter. We define this quantity, and then our final order parameter is the sign of this quantity. Okay, so we take the sign of the average, the difference in SR load times -1 to the n, where n is the beat number. And essentially, this keeps track of the phase of your alternans. So, for example, if you have spark, no spark, spark, you'll have +1. If it's spark, no spark, spark, no spark, you'll be -1. And that's why you take the sign. So we basically map our SR calcium concentration in the cell to an order parameter that tells us the phase of our response. So, for example, here we have spark, no spark, spark. Well, actually, this is also in phase. So for example, our order parameter will be 1 here and 1 here also. But let's say this out of phase, it will be -1 here. Anyway, so given this order parameter which measures phase, given this order parameter that measures phase, we simulate 1,000 by 1,000 system. Well, we try to go as large of a system as possible, and for this particular example, we looked at how this order parameter depends on pacing rate at steady state. So we're increasing our pacing rate as we go down, and we see that at low pacing rates, your system is essentially random. You have alternating response. You have stochastic responses, but it's essentially random. So your spatial average is constant. While as you increase your pacing rate, you begin to form domains of out-of-phase regions. Okay, and at very rapid rates, one phase dominates, and this is when you see the global alternans. Okay, so there's a very nice transition from random response to one particular phase. So here everything is black, meaning so in this case it was all +1. Everything was in phase at this pacing rate. So this is just a snapshot at steady state after. Oh, well, so we go down basically. So we go down. So in 10. So we go in 10. In 10 or 20 milliseconds, I forgot the exact details, from 300 all the way down to 200. So at 200 pacing rate, your system looks like that. At 300, you have alternating response to answer your question, but they're all random. So they're all out of phase, essentially. So you have a random distribution. And And okay, so the question is what happens as you go across this? And now we did a lot of simulations, and we determined that this transition has the features of an order, what's called an order-disorder phase transition. And some of the features of this phase transition are, well, the two features that we picked out are the correlation length. So basically, we can measure the correlation between these order parameters at different regions of our two-dimensional cell model, and we showed that the correlation length diverges as we approach the critical pacing rate, and this is indicative of a phase transition. Another feature is, for anybody who studied phase transitions, we see the phenomena of critical slowing down. So as you go closer and closer to the transition, which in this case is roughly around 266 milliseconds, you see that your order parameter as a function of beat number, your average order parameter as a function of beat number, it takes a long time to actually, well, there are a lot of fluctuations, and it turns out that as you get closer and closer to the critical pacing rate, the time it takes to sample your system diverges. So that's a phenomena of critical slowing down, which again is an indicative of a phase transition. So our simulations indicated that the transition that's happening here is an order-disorder phase transition. All right. So we wanted to understand in more detail the properties of this phase transition. So, the standard way of doing this is to apply what's called finite size scaling, and that answers your question of what is the system size dependence of your system. It depends obviously on system size, but it depends on system size in a very particular way at the critical pacing rate. So at criticality, these moments of our order parameter scale in a very particular way near a transition, and this behavior is well known in the theory of phase transitions. If you can fit your moments to a form to an equation of this form, then you can extract critical exponents from your data. And at criticality, you can extract three unique critical exponents. There's the beta, gamma, and nu, which you can get by studying the behavior of these moments. Okay, and these are very standard techniques which we just got from the literature on phase transitions, and essentially, I won't go into all the details, but effectively the first prediction is that the Binder cumulant, this quantity, has to intersect at the critical pacing rate. And we confirmed that in this model, and when we computed the exponents, we found that the critical exponents were very close to the critical exponents of the Ising model. Okay, and the Ising model is one of the standard models for phase transitions, and it turns out that this complex cell model where we're modeling each these arrays of junctions with multiple channels, it turns out that the critical exponents fit very nicely into this Ising framework. And I should give credit to Alain for in their 2009 paper, Alain and Juan actually pointed out that the system should exhibit Ising universality because of the symmetries of the problem, which I'll explain. May exhibit Ising, and we indeed confirmed in this very complicated set of stochastic ODEs, we confirmed that these exponents were Ising, and I just want to state that these were extremely tedious computations, because in order to get good estimates of the critical point, you have to average over about 1 million beats. Okay. And the simulation is being done over a time scale of 0.1 milliseconds. So basically, each of the simulations took months to do, and you might think does it really matter if you have to go 1 million beats to actually show what you're trying to show? Nothing on the physiological scale really depends on a million beats, but we had to do it just to show, for intellectual reasons, to show that the Ising model applied to this particular problem. So we wouldn't be able to reduce our error bars this low. In fact, this error is not as great as we wanted it, but we realized we'd need another 6 more months of computation to get there, but I'm pretty sure we would have done it. No. Well, without Gillespie, everything's deterministic. You just get a bifurcation. You don't get a phase transition, so it's completely different. You won't get any phase transition at all. It's a completely deterministic system. So the fact that we have this, the fact that there's this randomness here is coming from the stochasticity of the simulation. So, but that's a good point, because up to now, people had thought that calcium alternans are due to a peer doubling bifurcation. Here we show that it's not a bifurcation; it's actually a phase transition, which is different. I mean, you could model it as a bifurcation, but it's fundamentally not. All right. So there's still some open questions, which is what is the mechanism for the transition? And I won't really talk about this much, but another surprising thing is, the Ising model is an equilibrium phase transition. And the question is, how does a non-equilibrium system exhibit equilibrium critical exponents? Why is it modeled by an equilibrium system? Yeah, but you're far from equilibrium. No, there's no equilibrium in the cell. Yeah, but any biological system, especially the cell, is far from equilibrium, right? So technically, there's no reason why.
What definition of equilibrium is that? That would make it far from equilibrium.
I mean, you won't have energy transport in a cell to have if it's at equilibrium. Look at the difference in ion concentration across the cell membrane. There's huge differences in concentration. Your system is far from equilibrium. That's why it's so interesting. But we can talk about that later. But the cell is a far from equilibrium system, and the Ising model has no business actually showing up in a biological system, which is why we think this is interesting. But that's something that needs to be debated. All right. So the question is, we wanted to understand in more detail why this transition happened in this model, because as I said, it has been seen in several simulations. So what we decided to do was to reduce it to a very simple mapping model of just the basic features of calcium cycling. And it's the basic feature is the release of calcium, diffusion of calcium between nearest neighbors, and the uptake of calcium back into the SR. And we wanted to reduce it to a 2-dimensional simplified model to see what kind of transition we get. And the first thing that we built our system, our modeling on is this probability PS, which I'm going to call the probability that an L-type calcium channel opening induces a calcium spark. Okay, so it turns out in the simulations that the probability of inducing a calcium spark at a junction depends on the SR concentration. SR concentration is the calcium inside the SR. It depends on it in a very nonlinear fashion, and I'm going to explain to you where this arises from. And it's the fact that you have this nonlinear response that explains the why our system behaves the way it does. And this is directly from the simulations. Anyway, so we put this into a model, into a 2-dimensional model with release, uptake, and the release process is modeled with a probability function. So basically, I release with probability that's a function of my local variable. Okay, so this is basically a stochastic coupled map, a probabilistic coupled map, where we average over nearest neighbors. We have some simple model of uptake. The details are not all that important, but the key is the probabilistic release. and the spatial averaging. And with this model, again, we get the same kind of phenomena. We get global alternans even when your local response is completely probabilistic or stochastic. Okay, and indeed, even for this simple system, we checked the Ising exponents, and since we could do, for this case, we could do billions. We went up to 1 billion beats, not just 1 million. We went up to 1 billion beats, and we get exactly, effectively, almost exactly within error bars, the Ising exponents. So even the simple model where we have to reduce our system to just a set of coupled maps with the stochastic, with the probabilistic component, also exhibits this Ising transition. So this allowed us to understand really what's happening. So first of all, just to summarize, essentially, at rapid pacing rates, this probability curve, because it's a sigmoid function, it favors a local sequence of alternating responses. So your typical response is no release, release, no release with a particular phase, let's say +1 or plus, and out of phase. But that junction could also be could have a different phase where it's release, no release, completely out of phase with this, where it's -1. The fact that your release is stochastic favors desynchronization of these patterns, okay, while calcium favors the synchronization of the phase. And it's the competition between these two effects that lead to an order-disorder transition. And the fact that you have this Ising symmetry is what places the system in the Ising universality class. And the fact that you have effective short-range coupling in the system. And similar behavior has been seen in the early 90s. A lot of people had actually studied chaotic coupled maps and found phase transitions in those chaotic coupled maps. So this is sort of in the same spirit as those works. Okay, so now let me spend the last part of my talk trying to explain to you why is the local release at a dyadic junction, why is that release a switch-like function? Why is it sigmoid? Why is the probability function a sigmoid function? And actually, it turns out that we can easily explain that by simply modeling the stochastic dynamics of an array of RYR channels which behave. And we're going to simplify the Markovian model, so we only keep track of the closed open transition, and we say that the forward rate is regulated by the calcium concentration squared. Okay, and which is a lot of experiments have been done on the RYR kinetics, and people have found that it's very likely a power larger than 2. So I'm going to take it to be 2 just for illustrative purposes. But all my arguments will work, providing this number here. Actually, as long as this number is larger than 1, all my arguments will work. But 2 is likely the most likely number because it seems that there are 2 calcium binding sites on the RYR channel. So there's good reason to believe that the forward rate depends on calcium squared. Anyway, in order to understand the system, we basically write out the master equation for n RYR channels in the vicinity of a few LCC channels, and the master equation it can be written straightforwardly, where n is the number of open RYR channels, p is the probability that n of them are open at time t. The forward rate is given by using this formulation is given by how many channels that are closed times the concentration, the local calcium concentration, which depends on the number of L-type calcium channels open and the number of RYR channels open. Okay, so basically this is a driven stochastic system, and it's driven by openings of this channel, and the dynamics is for this variable n. Anyway, so there's a well-known method to analyze this kind of equations, and this is basically a standard driven nonlinear birth death process, and you can actually study the statistics of the system. And the key quantity to measure or to look at is what's called the effective potential. And the effective potential essentially governs the probability of finding X channels a fraction x open. So for example, so x is defined as n divided by n, is the number of RYR channels that are open. And by analyzing this function, you can determine the statistics of your system and how it responds. So basically, for relatively physiological parameters, we plotted the effective potential when the L-type calcium channel was closed. So basically, and it turns out that this parameter here was very important. It's called excitability. We'll call it the excitability of the cluster. When your cluster excitability is low and your channels are closed, then the probability your system is most likely to be closed where x is equal to 0. If your L-type channel opens, then your potential landscape will shift so that you have a minimum. So your system wants to go to the global minimum of this effective potential. So your system will try to open, but when the L-type calcium closes, your landscape goes back to this, and then your system will just return back to the closed state. Okay. However, when you increase your excitability of your system, a very interesting thing happens. There's a transition from monostability to bistability, and you go from when the L-type calcium is closed, from this landscape to this landscape. Okay, and because this is bistable, there's a stable point here and a stable point here. Because of this bistability, when your channel closes, you can remain trapped in the open state, and that's our model for a calcium spark. Because there's a transition from monostable to bistable, that naturally explains why our probability of sparking is a sigmoid function. So I can basically explain my sigmoid dependence based on the fact that my forward rate, so the key point here is the nonlinearity driving alternans in our problem is directly related to the fact that we have nonlinear signaling kinetics at the ion channel level. So that's the main take-home point, which I wanted to stress. So essentially, at least for this particular simplified system, we could understand exactly why alternance occurs and what is the nonlinearity that causes them. All right, so let me conclude. All right, so first of all, I've shown evidence that the calcium alternance transition in heart cells is an order-disorder phase transition. It has all the features of a classic phase transition: long-range order, divergent correlation length, critical slowing down, all of those things that if you studied phase transitions applies directly to the system. So we have good numerical evidence for that. And the fact that the alternance transition is dependent on the competition between the local nonlinearity and the diffusion between nearest neighbors, and that's what gives us the phase transition. Well, the fact that alternans have an Ising symmetry gives us the fact that it gives us the result that it's an Ising phase transition. And finally, the last point is that the local alternating response is driven by nonlinear signaling kinetics. It's a direct consequence of the fact that the forward rate from closed to open is dependent on the c squared. So as long as I put any power, turns out if I put any power larger than 1, it will work. You will get a sigmoid dependence, and technically you will get this transition. So we can actually relate it down to the details of the kinetics of the RYR channel. And so that's the picture that I'm presenting for calcium alternans. And that's it. Thanks.